Okay, so in the last session, we talked about binary search trees. I told you what binary search trees are and how we can insert and delete elements and search for elements and things like that. So generally, binary search trees are binary trees in which the left subtree of every element is smaller than or equal to that element, and the right subtree, everything in the right subtree is greater than or equal to this element. Now, today, we're going to do two things, hopefully, if you have enough time. The first thing is to implement binary search trees in C++. So most of today is a tutorial session. And then we're going to talk about this bad case that we saw in the previous session. So we saw that all the operations on binary search trees took OH time, where H was the height of the tree. But then I ended the session by showing you this bad case, where I'm inserting all the numbers in reverse sorted order or in sorted order. And in both cases, I actually end up with a tree that has a height of n. Now, of course, we know that we cannot get a height better than log n because it's a binary tree. So we will see some ideas for how to get heights that are just some constant factor times log n. So we'll end up with binary search trees that have a height of O log n. Okay. But I'm just going to start with implementing a binary search tree. So let me create a bst.cpp. Let's create our binary search tree. So the main difference between a binary search tree and a heap in terms of its structure is that when we had a heap with n items, since it was an almost complete tree, we could just use an array and we could say our items are in indices 1 to n. But here I cannot do that because in a binary search tree, of course, I might have some nodes that have both children. I might have a node that only has a left child. I might also have a node that only has a right child. So I have to implement binary search trees using pointers. And I'm going to create a struct, or let's say a class. And I'm just going to call it node. And this is going to correspond to one node of my binary search tree. Now, what do I want to save in a node of my binary search tree? I want to save a value. And for this particular case, let's say that my value is an integer. But in general, you can have any type of value as long as you can do comparisons between values. So I'm going to have a value. And then, of course, every node should have a pointer to its left child and a pointer to its right child. So I'm going to have a pointer called left, which points to the left child, and a pointer called right, which points to the right child. Now, I can also have a pointer to my parent if I want to, but in this case, I don't think that's necessary, right? But I mean, okay, let's just have the parent as well, just to make our life harder. So every node has a pointer to its parent, its left child, and the right child. And of course, if I'm the root, I don't have a parent, so my parent would be null. If I have no left child, then my left child would be null, and so on. Okay. Now, let's do these operations. And let's say that I also initially have a root. And let's say my root is null. Okay. I'm going to do the operations one by one. So let's first do the insert operation. Now, here's the thing. I can implement it in two ways. I can write it as a function inside the struct node, or I can implement it as a function outside. So you can do whichever you prefer. Let me actually do it inside. So let's say I have an insert function that takes some value x, and the idea is that I want to insert x in the subtree of the current node. Okay. Now, I just have to do what I was doing here in insert in the last session. I have to compare the value of x with the value at my current root. And based on that, I choose whether I have to go left or I have to go right. Okay. So I say if x is less than or equal to the value, let's say, I have to go left. Otherwise, I have to go right. Now, here's the thing. When I want to go left, I just check. If there is a left child, I recursively call insert on that left child. But let's say I was inserting 1, so I went all the way here and there is no left child. At this point, I have to create it, right? So pretty easy. I just say if there is a left, if left is not null, then insert this X in left recursively. Otherwise, just create a new node for this particular X. I don't know what to call it. I call it NX because it's the node of X. It's a new node. Now, the value should be X. It doesn't have a left or right child at the moment, but its parent should be the current node, right? And then I have to also say that the left child of the current node becomes this new node NX. Now, the same thing happens when I want to go right. So let's say I'm inserting 7, I'm at 6. I would just insert it in the right subtree. But if I'm, let's say, here, and I'm inserting, I don't know, another 5, there is no right subtree, so I would just create a right subtree. Or if I'm inserting another 6, let's say. So again, I say if the right exists, if right is not null, then just insert it in the right subtree. Otherwise, create this whole thing, create a new node. Let's say that the value of that node is X. The parent of that node is the current node. And that node is now the right child of the current node. Okay. So this is my insertion, and it just goes down the tree and inserts it. Now, I could, of course, write this outside. I'm just going to do it as one example, but for the other ones, I'm not going to do this. So I could have an insert like this. I could have an insert function that actually gets a pointer to the root of the tree that I want to insert in. Let's call it P. And it also takes some value X. Okay. Again, I do basically the same thing as here. I just have to compare the value at P with X instead of just value. So I say if X is less than or equal to P's value, then insert on the left. Otherwise, insert on the right. And my insertion is exactly right before, like before. I just check. I want to insert it in the left. I check, is there a left child? So if P has a left child, I just say in the left child, insert, oh, sorry. I say insert in the left child X. Otherwise, I have to create it. So the creation is basically this same thing. So I just create a new node. I say the value at this node is X. And I say the parent of this node is now P. And then I say P's left child is this new node. Right? And the right side is very similar. I'm too lazy to complete that. Okay. So this is insertion. Let me now completely remove this. We already have this insert. Nice. Now, the other thing we had was searching. So again, I give you a pointer to the root of the tree, and I give you a value that I'm searching for example, 11, and I ask you, is 11 in this tree? And you just have to, again, start comparing it with the root value. Based on that, decide whether you go left or right. And if you get the exact value you're searching for, you return true. If you don't, if you get to a null pointer at some point, you return false. So I have a Boolean function called search. It's searching for X. I first say that if X is the same as the value at the current node, then just return true. Now, of course, instead of just having a Boolean function, I could have a function that returns a pointer. It could just return a pointer to the current node. But I'm just thinking of a search function that says yes or no. Okay. Now, otherwise, just check. If X is less than the value of the current node, you have to search in the left. But you have to first check, does the left exist? Is there a left child here? If there is no left child, you just have to say false. So if x is less than the value, if left is null, return false. Otherwise, return left search x. Now, same thing for the right. So if x is supposed to be in the right child or in the right subtree, I say if there is no right subtree, return false. Otherwise, search in the right subtree for the same x and return it. Okay. So you see the implementation is actually quite easy. Now, of course, instead of this, I could have a search function that returns a pointer if the element exists and returns null if it doesn't exist. So I can turn this into a node star, so it's returns a pointer. So if I find the value at the current point, I would just return this, which is a pointer to the current node. And if x is less than the value and left is null, otherwise return the result of the search. And here it's also the same. Instead of false, just return. Okay. So this is our search operation. Let me just compile to make sure everything works right now. It seems so. Okay. Nice. Now I have insert and search. Now the next one was remove, but before writing remove, I want to write some other operations because remove was actually the most complicated one, and I want to be able to use these previous ones. So I had a sort operation, which basically printed all of the numbers in my binary search tree in a sorted order. And we said that this is the same as the in-order traversal. Like you start, you always print the left child first, then print the current node, then print the right child. So I can just have that. I mean, again, I can have a function that returns a list, but I can also have a function that just prints it. And I'm lazy, so I'm just going to have a function called sort that prints it. Now, this is super easy. I say if there is a left child, print the left child and its children recursively. So if left is not null, just do left sort. Then print whatever you have at the current node. So just write the value, the current node. And then if there is a right child, do right sort. So print everything in the right child sorted order. Okay, at this point, we have enough to write a simple sort. So let's do that. So let's say I read some number A, and then I have to read n numbers and insert them. Now, one pesky problem is that my insert doesn't work for the first one. So for the first item, I have to actually create it. But that's fine. So I say for I from 1 to n, read some number x and add it to my tree. But the problem is that initially my root is null. So I don't really have a tree. And if the root is null, I just create a new node. And I say this is now my tree. And then the root's value would be x. That's the first insertion. Nothing special about that. Otherwise, I just say in my root, insert x. Right? So that's the insert part. And then I want to sort everything. So I just call root sort. And it should print all the numbers in sorted order. Let's say I give it 6 numbers, 1, 2, 3, 4, 5, 6. And it doesn't work, as usual. Okay. So what's happening here? Let's see where our bug is. We are reading the numbers. If root is null, we make it into a new one. Otherwise, in the root, we just insert x. Let's go into our insert. When we're inserting x, if x is less than or equal to the value, we try to go left. If left is not null, we just say left insert X. Otherwise, we create a new node. Its value becomes X, its parents becomes here, and left is NX. It seems this is right. If right is not null, right insert X, node star NX new node, NX value NX. Yes, right NX. Okay. Left sort, write the value. If right is not null, right sort. Okay. Let me just see what's happening. Let's say comparing with value. And here I just write left. There I write right. You're going to see a lot of debugging in this course. So 6. So 9 is just inserted. 8 goes to the left of 9. So let's actually draw what's happening here. So originally I have 9 here, and then I have 8 to the left of 9. And then 5 goes to the left of 8, which is here. Then I do 2, goes to the left of 5. And then I do 10, goes to the right of 9. And what was my last number? 47. Goes to the right of 9 and the right of 10. So 47 is here. It seems our insertion is working correctly. So why is it that when I do root sort, it doesn't print it correctly? So when I want to do sort, I say if left is not null, try going left. Then write the value at the current node. And if right is not null, then try going right. Am I missing something? Wait, this is weird. Let's see. So here, every time I'm doing this, I'm going to say going left. Actually, before this, I'm going to say going left. And then here, I'm going to say going up. And here, I'm going to do the same thing. Going right. And going up. Let's see what's happening. So 6, 9, 8, 5, 2, and 47. Okay, comparing with 9, right? Okay, it goes left to what? This makes no sense. What's happening in insert?
Like when you follow the function on the is created no matter the left.
Oh, right. Oh, yeah, there is an else here. Yeah. I don't know why I was doing that. I wasn't thinking about that, but that's wrong, yes. And here also there is an else. I was thinking this is, yeah, okay. Now, yeah, I'm always writing buggy code. And the easier the data structure, the more likely that I write a buggy code. Let me remove that. And let's say, again, 6 numbers. What were my numbers? 9, 8, 5, 2, 10 and 47. Yes, thanks. Yeah, that was a really stupid bug. But now I don't have it anymore. Great. Okay. And let me remove all of these. Okay, so we have all of these now, and hopefully it works. Now, let's go back here. So we also had these two operations, min and max, which basically return the smallest element and the largest element. And again, I can implement min as taking a pointer to some node and then returning the minimum element in the subtree of that node, right? So I'm going to have min. And again, this can be a node star, or it can just return the value. It doesn't really matter. So here's what I do. I say, when I want to find the minimum item, I want to try moving left as far as possible. So if there is a left child, go to the left child and return the minimum there. If there is no left child, this is the minimum, right? So if left is not null, just return whatever minimum you have in the left subtree. Otherwise, return what you are. So return this. Okay. Min is the simplest thing ever. Okay. Now max is basically the same thing, except that we're moving right. So I say if child, go to that right child and ask it for its minimum element. Otherwise, just return this. Okay. So min and max were quite easy. Now, here's another operation that I would like to do. I want to be able to find the next element. So I give you a pointer to some element. For example, I give you a pointer to, let's say, 7. And I ask you, what is the next larger element? So the smallest element that is after this 7. That's what I'm asking for you. What is the next element? Now, let's try to visualize this. So I want to do next element. And let's say I have some pointer p, and I want to find the next element after p. Now, where can this next element be? Look, there are several cases. First of all, let's consider the case where p has a right child. So there is a right subtree here. And let's say I show the subtrees with triangles. So there is a subtree here. I claim that if there is a subtree to the right of p, then the minimum element of that subtree is the element right after p. Okay. Now, why is this the case? Because, well, all the elements in the left subtree, if they exist, are smaller than or equal to p, so I don't care about those. And let's say all of my elements are distinct, so all of the elements to the left are smaller, right? Now, consider p's parents or p's ancestors. Let's say p was the left child of its own parent, right? Now, what does this mean? This means that p and all of its descendants were smaller than this parent. So, of course, if I'm going to find the next element after p, I have to look here, because it has to be an element that is smaller than this parent, right? And the same thing happens if p was the right child of its parent. So if p was the right child of its parent, then, well, p is bigger than its parent. So all the elements in the subtree of p are also bigger than its parent. So of course, I shouldn't go back up. I have to just find the smallest element here. I talked about this for just the parent of p, but you can do the same kind of analysis for any ancestor of p, how many levels above it is, right? So when I'm finding the next element of P, the easy case is when P has a right subtree. In that case, I would just return the minimum element in the right subtree of P. What if P doesn't have a right subtree? So let's see, do we have an example of this here? Yeah, so let's say I want the next element after 19 here. And 19 doesn't have a right child. Any ideas? Now, in this case, I claim that the next element is definitely one of the ancestors. Okay. Now, there are two ways to figure this out. One way is to look at our sort function, right? If you look at our sort function, we said that this prints everything in sorted order. And actually, I can apply it in both cases. If I just trace what my sort function does, if my P has a right child, my sort function prints the minimum element of the right subtree right after P. So that's the next element. But what happens if P doesn't have a right child? So this part of the code doesn't get executed at all. So I print P, and then what happens? This is the end of this sort function. So I go back to the parent function that called this one, but that one was on the parent of P, and so on, and I keep going up. I will never go to the right again. So the next element has to be one of the ancestors of P. But can we look at this without the sort function? So let's say I have my element P here. Again, P is a pointer to one of my elements. And the eraser doesn't work. And it doesn't have a right subtree, right? So let's look at its parents. I want something that is bigger than P. So first, let's consider if P is the left child of its parent. In this case, I claim that the parent is exactly the element after P. Okay. Why is that? Because if you just look at the structure of the tree, everything that comes to the right of the parent is definitely bigger than the parent. But the parent is bigger than P. So I wouldn't have to worry about this part, right? And then for everything that comes above the parent, I can again do a casework. I can say if the parent is the left child of the grandparent or the right child, but in any case, they will all follow the same trajectory and they will show that this parent is the next side. Now, but the other case is this. It's when P is the right child of its parent. So it means the parent was smaller than P. So I have to keep going up. I have to look at the grandparent. Maybe the parent was also the right child of the grandparent. In this case, I have to just keep going up. So I keep going up until at some point I go right. Well, I mean, at some point there is an ancestor that is the left child of its own parent, right? And then this means that all of these parts, everything here is in the left subtree of this node. So everything here is smaller than this node. But this P is the largest element here. So this node is exactly the next element after P, right? So this gives me a little bit more information than the sort, in the sense that instead of just going over all the parents and not knowing when to stop, I can stop as soon as I see there is a parent that is the left child of the higher level parent. I don't have the vocabulary for these things. There is an ancestor who is the left child of the higher level ancestor. And as soon as that happens, I just return this one. Okay. So let's do this. Let's say I just call it next, and this is supposed to return the next element. Okay. I say if the right is not null, if I have a right child, then just return the minimum element in my right. I can just use the min function that I already have. Otherwise, if I haven't returned yet, it means that my answer is in one of my parents. So I just keep going up, okay? So let's say I take some p, which is originally just my parent. And actually, let's just keep 2 pointers. I keep a pointer. Okay, sorry. So let's say the current node is p, the parent is q. Okay. And all I'm doing is asking, is p the right child of q or the left child of q? Okay. If p is the left child of q, so if q left is p, then I should just return q, because I'm in this situation where I have q here and p here, right? And let me just do a while loop here. So I'm going up the tree and I'm doing this. Otherwise, if p is the right child of q, I just go 1 step up, right? So p becomes q, q becomes q's parent. And I do this as long as I have not reached the root, right? While q parent is not known. And of course, when I reach the root, there's nowhere to go. Now, here's the thing. This function does not always return. Does not always return something, of course. So in this case, I know that I had a right child, so I'm just returning the minimum element in the right subtree. That's fine. And then these things are easy. P points to the current point, Q points to the parent. I just ask. If I'm at the left child of the parent, I return the parent. Otherwise, I move both of them up. Actually, it would have been easier to write it like this. Maybe it's easier to visualize like this. So I'm moving both P and Q up. Okay. And I continue this until I get to the root. And if I ever find that Q is the left child of, P is the left child of Q, I just return Q. But there is a case where this never happens, right? So I start at P, I look at the parents, and I see that all of the parents are smaller than P. So P was the right child of its parent, the parent was the right child of the grandparent, all the way to the root, right? So what happens in that case? Yeah, in that case, P is our maximum element. So there is no next element. So because there is no next element, I'm just going to return no. Okay. Now, of course, I can write a similar function that finds the previous element. Finding the previous element, you can again do the same kind of argument, and you can say if there is a left subtree, I have to definitely print the maximum element of the left subtree. But if there is no left subtree, I have to go up in the parent and find the first place where I'm in the right subtree of the parent and then print it. I'm not going to write that one. It's just a mirror image of this one. Okay. But now let's do another operation. And this is actually quite an interesting one. So let's say I call this operation rank. And rank x should return the number of elements that are less than x, or less than or equal to x, let's say. Okay, returns the number of elements in my binary search tree that are less than or equal to x. Now, generally, let me see. When I was doing the insert, I said that if the value is equal, insert in the left, right? So equality is broken in favor of left. But yeah, let's just imagine we don't have repeated values, then this becomes very valuable. Okay. So if I give you some number x and I ask you how many of the numbers in your binary search tree are less than x, how do you find that? So for example, let's say I have this binary search tree, and the number I give you is, let's say, 18. I ask you how many elements here are smaller than 18. So this is actually very similar to search, right? I can start at the top here at 12. Actually, let me copy this and just put it somewhere else. So, by the way, this is why I'm not using a traditional board. I want to be able to copy. So let's say I'm just asking for the rank of some value, and let's say that value is 18, right? So I start at 12, and let's say I'm doing something like the search for 18. So I see that 18 is larger than 12. What does this tell me? It tells me that not only 12 is smaller than 18, but also everything in the left subtree of 12 is going to be smaller than 18. So I know that, I know that all of these are going to be in my answer, right? Then I go to the right. I see 100. 100 is not in my answer, right? Because 100 is bigger than 18. But maybe there is something in the left subtree of 100 that is in my answer. So I have to then go left. But then I see that here there is also nothing. So if I want rank of 18, that's just 1, 2, 3, 4, 5, 6, 7, 8. Right. Now, okay. Let's say instead of rank of 18, I was doing rank of 21. Again, it would start similarly. I compare 12 and 21, and I see that 12 and all of its left subtree are in my answer, right? Then I compare 21 and 100. I see that 100 is larger than 21. So I know that nothing in the right subtree of 100 answer, because everything on the right subtree is bigger than this number. So I have to just search the left subtree of 100. And there I also find 19. So the answer for 21 is 9. Okay. Now, in general, this is great, because whenever I'm at a particular point, either I'm going right, in which case I know that I have to include this node and everything to its left in my answer, or I'm going left, in which case I'm just continuing my search, right? But the problem is that I don't want to go and count everything in the left subtree. So instead of doing that, I would just save some extra information. So let's say I have this tree again. At every node, I also remember what is the size of the subtree rooted at this node. So how many descendants does this node have? Plus 1 for itself. I count the node as a descendant of itself. So the subtree here has size 1. Oh, this is a terrible color. Let's say green. So at all of these leaves, the subtree size is 1, right? Here, the subtree size is 3, because it's just 1 plus 1 plus 1 for here. Here, the subtree size is 3. Here, the subtree size is 7. Generally, the subtree size at every node is the subtree size at the left node plus the right plus 1, because I have this node itself as well. So I have 1 here, I have 1 here, I have 3 here, 3 and 7 is 10, I have 11 here. So let's say I keep track of these subtree sizes. Now, if I want to answer a rank question, it's much easier. So let's say I want to ask for rank of 11. Okay. And by the way, my number may be in the list and maybe in the binary search tree or not. I don't really care. So I compare 11 and 12, and I see that 11 is smaller than 12. So anything in the right subtree of 12 is definitely not in my answer. So I don't have to care about the right subtree. I just go to the left subtree and I ask there. I compare 11 and 9. I see that 11 is larger than 9. So I know that 9 and all of its left subtree are definitely in my answer. They're all smaller than 11. But I don't have to count them one by one, because here I have their number, it's 3. And there's, of course, 9 itself. So I have found 4 numbers that are smaller than 11. And then I continue my search on the right side. I compare 11 and 10. I see that 11 is larger than 10. So 10 and everything in its left subtree are going to be in my answer. And so again, these are in my answer, but I know the size. I know that the size here is 1 plus 1 for the node that I had here. And then finally, I go to the right and I find 11. So that's how I find my rank. And again, the time that I'm spending to find the rank is also OH, because I'm starting at the top of the tree and just going down. And whenever I'm going left, I'm not adding anything. Whenever I'm going right, I'm adding the size of the left subtree. Right? Okay, so let's implement this. So let's say I want rank for some particular x, and this is basically the number of elements less than or equal to x. Okay. I have to compare x with the value of the current node. If x is less than the value of the current node, I know that the current node and the right subtree are not in my answer, so I just have to return left rank x. Okay, but again, you should always think, does the left subtree even exist? Right? Because maybe I'm at a node, I'm searching for something, the x that I'm searching for is less than the value at the current node, but there is no left child. So in that case, there is nothing that is smaller than the current node. So I have to say, just check. If left is null, then return 0. Otherwise, return left rank x. Okay, I can also write this with an if, but I'm too lazy. Okay. Now, the other case is when x is exactly equal to the current value. So if x is equal to the value right now, what does this mean? This means that I have to count the current node, and I have to also count everything to the left of it, right? So my answer is just going to be 1 plus the size of the left node. So I say left. Let's say I have a size. Okay, I will write that size later on. So this size is going to give me the number of elements in the subtree of the left node. Okay, but again, here I have to ask, is left null? If left is null, then you have to just return 1 because it's only this node. Otherwise, if there is a left, return 1 plus left size. Otherwise, what if x is exactly equal to the value? Sorry, what if x is bigger than the value? Now, again, I have the same answer as before because all of these nodes are definitely there. So I say first, take everything that is in the current node and everything that is in the left subtree. So again, this is just saying if there is a left subtree, sorry, if there is no left subtree, there is only one element, which is the current node. And if there is a left subtree, then 1 plus left size. But now I have to also do a search on the right subtree, right? But again, I have to check if there is a right. If right is not null, increase the answer by the rank of x in the right subtree. And then just return this answer. Okay. Now, this is all great if I can have the sizes of my subtrees. And the sizes of my subtrees are basically these numbers in green that I wrote here. Now, I have to do that as well. So I'm going to have another integer here called size, which is basically going to be the number of nodes in the subtree of the current node. Okay. Now, I have to be very careful about size. Let's go everywhere in our code and see when we have to set the size. So when I'm creating this new node here, the size is 1. Right, and then I have to look at insert. I don't have delete right now, so only insertions are going to change the size. because I mean, search is not changing the tree at all. Sort is not changing the tree at all. The only thing that is changing my tree is insert. So let's do insert. So in insert, every time when I'm inserting this X in the subtree of the current node, I have to also increase the size of the current node. So I also do size increase, right? And also when I'm creating a new node, I have to be careful that its size is always 1, right? So whenever I'm creating a new node, I set the size to 1. And that's it, right? So now I have the sizes, I have the rank. How much time does this rank function take? Now, first of all, I'm not really spending any extra time on size because I just took my insert, and at every level of the insert, I just added one extra operation that is just updating the size. So my insert remains the same asymptotic runtime as before, which is OH. But now when I want to find rank, this is also OH, because at every node, I'm doing a constant amount of work. Remember, asking for left size, that's constant now, because I already have it. And then afterwards, I'm either asking the left child for the rank of X, or I'm asking the right child for the rank of X. So I'm starting at the top and just like search going down the tree. And I can go down at most H times, where H is the height of my tree. So this is also OH. Great. Now that we have all of these things, we can finally do remove. But here's the thing, doing remove with rank is a bit hard because you have to update all the sizes. That's why I waited to add rank first and then add remove, because I want you to suffer as much as possible. So let's now do remove. Where should I write this? Let me, okay. Doing remove, I can just assume that I've been given a pointer, right? Because what's the point if you don't have a pointer? Like, what kind of removal are you really doing? Like, you can always do search first, and if the item doesn't exist, you don't have anything to remove. Otherwise, you have a pointer to it. So, and remember, my search is now returning a pointer. Where is search? This is search. So whenever I'm removing something, I can just assume that I've been given a pointer to it. So let's say this is remove. And I'm also assuming that my remove does not make the whole thing empty, because you have to also take care of that case separately. But let's say that my remove is just saying remove the current node. And I'm also sure that my tree is not becoming empty after removing the current node. Okay. Actually, I can check for that case where it becomes empty. So I can say if the current node is the same as root, and if there is no left child and no right child, then just remove everything. But let's not do that. Let's just say I want to remove some elements. Now, what was our algorithm for remove? You see, we talked of basically 3 cases. One case was this, right? When I'm removing something and it doesn't have any children, I can just remove it. So let's first do that. So I say if left is null and right is also null, just remove this node. Okay. Now, how do you remove this node? I would remove it by just disconnecting it from its parent. Okay. So I say if parent's left child is this, then parent's left child becomes null. Otherwise, if the parent's right child is this node, then the parent's right child becomes null. Okay. And again, I'm assuming that there is a parent here, right? So the only case where I wouldn't have a parent here is if I'm removing the root and also the left child and the right child are null. I said I don't want to cover that special case where the tree becomes empty. Because when the tree becomes empty, it's just empty. You can just have a counter, you can know that it's empty. Okay, so that's fine. Now, the second case was when I have only one child. Do I have a node with only one child here? No. Okay, let's say here. Let's say I wanted to remove 10. Okay. Here, what we said was that, again, we just remove it and we put the single child as the child of the parent. Okay. So I say if left is null or right is null, which means that exactly one of them is null because I already covered the case where both of them were null. Now I'm going to, so this one is this one is parent. I'm going to call this one child. Okay. So I'm going to say I have the child, and what is the child? If left is null, my child is just going to be right, otherwise my child is going to be left. Okay, so child is just a pointer to whichever child exists. Okay, now what do I want to do? I want to remove the current nodes and just connect the child directly to the parent. Okay, so here's what I do. Again, I have to check. I have to say if the current node is the left child of the parent, then the left child of the parent becomes the child, and the child's parent becomes the parent. Otherwise, if the current node is the right child of the parent, I don't need to write this, but I'm just writing it anyway. Then the parent's right child becomes the child, and the child's parent becomes the parent. So basically, all I'm doing is that I'm removing this one, and I'm making parent directly recognize the child and child directly recognize the parent. Okay. So that's that one. Great. But of course, I can also deallocate the memory that I had. I don't really care about that. I just disconnect this node from everything and I let it float. I don't care about optimal memory management in this course. But yeah, you can also do delete this at the end. So you can have something like this. Okay. But now the other really important point is that the sizes actually change. When you're removing something, the size of the subtree of all of its ancestors are going to change. But I'm not going to go there yet. We still have another case. And the other case is when I'm removing something and it has both of its children. So, okay, let me go to this example here. Let's say I'm removing 100 and it has both children, right? So the solution that we had last time was to just find the next item after 100, swap them, and then remove that item. Okay, so I'm going to do this here. Okay, left is null or right is null, else. So this is the case where left is not null and right is also not null. What am I going to do? I'm just going to say, take the first element after this one. Okay, so this is my next element. And I can just call the next function, but in this case, I know that I have a right child. So I can just take the minimum of the right child. It would do the same thing. I can just say n is next of the current node, or actually, was it called this next? Where is my next function? Yeah. I can say this, or just next. Or I can say, take the right child and give me its minimum. Same thing. Okay. So this is my next node. And now I'm going to swap the values of the current node and the next node. Okay, so swap the value of the current node and the value of the next node. Now I'm sorry. I could just write value here, but I want to really emphasize that I'm swapping the values of these two, right? And after I swap the values, I say remove that next node. So this is what's happening here. If I want to remove, let's say, 12, I first find the next node after 12, which is 19, right? It's the minimum in the right subtree of 12. And then I swap 12 and 19. So I just swap the values. I will have 19 here, and I will have 12 here. Okay. And then I remove this node. But remember, I've only swapped the values, so this is actually pointing to the place that has to be removed. NE is pointing to the place that has to be removed. This is NE, this is this. Okay. And then I just remove this NE. And we've seen before that this preserves our binary search tree. Okay, great. We did all of these things. This is now our remove function. And again, it works in OH as we've seen before. Now the question is how to update the sizes. We have to make sure that all of the sizes are correct. Right? And this is like the most pesky part of this. When you have extra information in your tree, and when you remove something, or when you insert something, you have to make sure that you update that extra information, in this case, the size. So here's the thing. If I'm removing this current node, which sizes are going to change? The sizes of all of its ancestors, right? So for all of the ancestors, the size is going to decrease by 1. I have to just update the size of every ancestor. Okay, so here's what I can do here. In this case, I just say, let's say I have a function called update size, and I just call it on the parent. I say parent update size. In this case, again, I do the same thing. I just say parent update size. Because for the child, nothing happened. It has the same subtree as before. It's just the parents whose subtrees are changing. And in this case, I actually don't need to do anything because I'm calling remove, and then it's going into one of the previous cases, and it's going to call update size anyway. Now, here's the update size that I'm going to write. Update size just says that the size becomes the size of the left child plus the size of the right child plus 1, right? So size becomes left size plus right size plus 1. But again, we have the usual problem. Maybe left doesn't exist. If left doesn't exist, I have to put 0 there. Maybe right doesn't exist. In that case, I have to put 0. So I just say, we start with this. If left if left doesn't exist, let's say size is 0, otherwise size is left size. Then increase the size by 1 for the current node. Then if right doesn't exist, fine, I don't need to do anything. Otherwise, size increases by right size. So I can just write this like this. I'm trying really hard not to use the question mark again. So yeah, that's the update size. But when I update the size of some node, I have to call update size on the parent as well, because I have to cascade all the updates up the tree. So here I say if the parent is not null, because again, you have to remember the parent might be null as well, then just do parent update size. Now, instead of all of this, I could just have a for loop that goes up the tree and decreases all the sizes by exactly 1, because when I'm removing, I know that the size of all the parents are going to be decreased by exactly 1. But I'm going to do some other things later on, which are actually worse. And then I would need a function like this. Okay, great. Now we have rank, we have remove, we have sort, and hopefully I don't have any bugs in this code. I will look into it and debug it and put it on canvas if there is something wrong. But But now we're going to go back to our main problem from before, which is this idea that everything took OH time. And in the worst case, H would become n minus 1. I could have a tree of height n minus 1. And that's awful. I don't like that. Right. So we're going to talk about kind of an extension of binary search trees, or a special case of binary search trees that ensure that the height is always logarithmic. Because if I can do that, then I can be sure that I can do all of these operations in O log n time. And by the way, this is much more powerful than the heap, because in a heap, I could just insert and I could remove the maximum element. Here, I can do search. I can find the next element. I can count the number of elements that are smaller than some elements. So I have so many other operations here. And all of them are being done in OH. So if only I can reduce H to be log n or some constant times log n, I'm really happy. Okay. And the idea that we're going to see is an AVL tree. And AVL is based on the names of the people who actually invented it for the first time. Sorry, this is the L. So it takes 2 letters from Adelson-Velsky and 1 letter from Landis for some reason. It should have been AL. But yeah, this is the original paper. It was a Soviet paper in 1962 that came up with this idea. And now we're going to see the idea, and hopefully in the next session, we're going to code it. So the idea is very simple. We want our tree to be balanced, roughly speaking. We cannot always have a perfectly balanced tree. Unfortunately, this is not a heap. This is much more expressive than a heap. So instead, what I'm going to do is I'm going to take each one of my nodes, and I'm going to assign some extra information to it. And the extra information that I'm going to use this time is just going to be the height of the subtree rooted at that node. Okay. So I'm just going to assign a height to every node. Assign a height to every node. For the leaves, I would say the height is 0. Okay. And for any node, the height is 1 more than the maximum of the heights of the 2 children. So basically, the height of a node is the length of the path from that node to the farthest possible leaf in its subtree. Okay. So I'm just going to write the heights here. This one has height 0. This one has height 0. This one has height 1. This one has height 0. This is also height 0. This is height 0. This is height 1. Has height 2, because the height is the maximum of the height of the 2 children plus 1. This one also has height 2. This one has height 3. Okay. Now, we say that our binary search tree is an AVL tree if for any node, the difference between the heights of the left child and the right child is at most 1. So for any node, I want to make sure that I have the same height on the left and on the right. That's basically saying that the tree should be balanced, right? But I cannot say that they should be exactly the same. So I say they can differ by at most 1. So this is the AVL property. For every node, let's call it n, we should have the height of the left child minus the height of the right child is going to be at most 1, the absolute value, less than or equal to 1. Okay. So for example, this is an AVL tree. I didn't intend it to be, but it just turned out to be an AVL tree. So for every node that you look here, the left and the right children either have the same height or their heights are different by exactly 1, right? So here the right subtree has a height of 1, the left has a height of 0. Here it's the opposite. But the difference in the height is at most 1. So this is called an AVL tree. Now, what do we want to do? We want 2 things. First, we want to prove that if we have an AVL tree, its height is going to be logarithmic, because otherwise, what's the point? Right. So I'm doing all of this because I want to be able to do all of my operations in logarithmic time. So if this property doesn't give me logarithmic heights, I don't like it at all. So the first thing I'm going to prove is that if I have an AVL tree, its height is O log n. Now, the second part, which is much harder, is to make sure that my binary search tree always remains an AVL tree. So every time that I'm inserting something into my binary search tree, or every time that I'm removing something, I have to change the tree in a way to make sure that it remains AVL. Because, for example, these bad trees that we had here, they're definitely not AVL, right? So here, the right subtree has a height of n-2. The left subtree has a height of, well, it doesn't even exist, right? So, oh, by the way, what height should we give to a non-existent subtree? Let's give it a height of -1, right? That makes sense, because if I just have one leaf, I'm giving it a height of 0. So you can imagine that this leaf has 2 children, especially in our implementation, and both of those children are basically null, right? But if they're null and their parent has a height of 0, that means that the height of null should be -1 for everything to just work out. So null has a height of -1. This is -1. This is -1. These are all -1. Okay. So I'm going to have the AVL property like this. Now, the theorem that we want to prove. We want to say every AVL tree with n nodes has O log n height. Okay. Or more specifically, I want to find a constant such that my height is at most that constant times log n. Okay. Here's how I'm going to prove this. I'm going to say, let's look at the worst possible tree of any given height. So what is the worst possible tree you can have of height 0? It's just one node, right? And I say worst possible tree in the sense of having the least number of elements. So if I want to be really wasteful, let's say someone asks me to create an AVL tree of height h that is as wasteful as possible, has the fewest number of nodes. How wasteful can I be? Right? So I'm going to show that with, let's say, n sub h. So n sub h is the minimum possible number of nodes in an AVL tree of height h. Okay. Now, n0, if I have a height of 0, I have to have at least one node, right? What is n1? What is the worst tree that I can have with a height of 1? With a height of 1, tree that looks like this, right? Of course, I can also have a tree with 3 nodes, but I want to take the tree that has the minimum number of nodes and has height 1, so n1 is 2. And similarly, you can calculate n2, n3, and so on. In general, what can I say about nh? If I have an AVL tree of height h, what does that mean? This means that I have the root of my tree. This is my root. And this is at height h, right? Now, by definition of height, if my root is at height h, it should have at least one child that is at height h minus 1, right? Now, I don't care if it's the left child or the right child. There is at least one child that has height h minus 1. Now, what can the height of the other child be? Again, here the distinction between left and right is not important. I have one child of height h minus 1. What are the possible heights for the other child? Yeah, it cannot be more than h minus 1 because the height of the root is h minus 1. And it cannot be less than h minus 2 because the AVL property says that the left and right children can be different by at most 1. So the height of this other child is either h minus 1 or h minus 2. But if I want to have the minimum number of nodes in there, I would choose h minus 2, right? So in any case, the number of nodes in a tree of size h is going to be at least 1 for the root plus n of h minus 1 for this node, this is h, plus n of h minus 2 for this node. So this is the inequality that I'm getting. N of h is at least 1 plus n of h minus 1 plus n of h minus 2. Okay. Now, here's the thing. Let's be really good computer scientists. And let's try to just find a bound on n of h. Look, I'm saying n of h is at least this much. But here's the thing. Do you agree that if n of h is greater than this, then it's also greater than 1 plus 2 n of h minus 1? Because if I have a tree of height h minus 1, I can fit more into that than a tree of height h minus 2. That's kind of obvious, right? And I also don't care, plus 2 h minus 2. Yeah. Right? So I want to say n of h is greater than something. It was greater than this, but instead of n of h minus 1, I'm putting something smaller, which is n of h minus 2. Okay. Now, I don't want to care about the 1 either. So all I know is this, n of h. So the number of nodes that I will have in a tree of size h is at least twice the number of nodes that I will have in a tree of size h minus 2. Right? So this means that and starting with these values, it means that the number of nodes that I have in a tree of size h is at least 2 to the power of h over 2, right? Because every time that my height is increasing by 2, my number of nodes are doubling. So this means, if you just solve the recursion, that n of h is more than 2 to the power of h over 2. Okay? Or I can also use the omega, but it's hard to write omega by hand. Okay. Now, if this is the case, what did I want to say here? I wanted to say that the height is at most the logarithm of the number of nodes. But what did I show? I showed that the number of nodes is more than 2 to the power of height over 2, right? So this means that height over 2 is greater than or equal to the log of the number of nodes, right? Again, this N and H are really bad choices. I should have gone with depths and D. So height over 2 is greater than or equal to log of N. I mean, it's N sub H, of course. But that's fine, right? So my height is at most 2 times log N, right? So height is greater than or equal to, oops, no. This is the opposite. I'm so bad. Height over 2 is less than or equal to log of NH because I'm taking log of both sides. I don't know why I swapped the order, but didn't swap that. And then, so height is at most 2 log of NH. I should never do any kind of basic algebra there. Okay. So my height is at most twice the logarithm of the number of items that I have. So of course, my height is in O of log N. And actually, the constant that I found was 2. So my height is at most 2 times log N. But we can do a better analysis in the sense that I can improve the constant. I can do better than 2. So here's the thing. Let's just take the same recurrence that we had here. This is all we knew. We knew that n of h, which is the minimum number of nodes that I can have in a tree of size h, in a tree of height h, is at least 1 plus n of h minus 1 plus n of h minus 2. What does this remind you of? Yes, this is very similar to the Fibonacci recurrence, except that I have a 1. But I don't care about that 1. I can just ignore it. I'm just saying that n of h is greater than something. Of course, I can just ignore the 1 there. So I can write this. I can instead say that, oops, okay. So I can say n of h is greater than or equal to n of h minus 1 plus n of h minus 2. Right? And I mean, my base cases are basically the same as Fibonacci as well, maybe like shifted by 1 element. So all this shows me is that n of h is actually greater than or equal to the h's Fibonacci number, right? But you know that, I mean, hopefully you know this. If you don't know, just look on Wikipedia. This is actually in theta of the golden ratio. Let's show it phi to the power of h. Right, that's the solution for Fibonacci. And phi is like 1.6 something. I hope so. Anyway, if n of h is greater than f of h, again, I can do the same thing. I can say n of h is in omega of the golden ratio to the power of h, right? So now I do the exact same thing that I did here. And what I would get is actually, well, you have to look at the log of this golden ratio and so on. It gives you a better constant, okay? So we get, I think h is less than 1.4 something. I don't remember the exact log value, times log of nh. So our height is actually logarithmic, but the constant is not 2, it's like 1.4 times log of n. But I mean, as long as you're only interested in asymptotics, it doesn't matter. All you care about is that your height is O log n. And of course, your height cannot be asymptotically better than log n because it cannot be less than log n in any case. So your height is exactly theta log n, right? There is a constant hiding there. This simple analysis shows that the constant is at most 2. But yeah, instead of this analysis, you can just analyze it with the Fibonacci numbers and you get that the constant is 1.4 something times log n. Okay. Now, the remaining question for the next session is how do we make sure that a tree actually has the AVL property? So all I've shown you until this point is that if I have a binary search tree that additionally satisfies the AVL property, then that's a good binary search tree. It has like logarithmic height. But how do I make sure that the generic binary search tree is actually an AVL tree? So I have to go back and I have to change all of the algorithms that change the tree, which is basically the algorithm for removing one node and the algorithm for inserting one node. I don't need to change anything else. So I have to change insert and remove in a way that they make sure my tree is always an AVL tree. And right now they don't do that. So we will see in the next session how to make this work. And again, as one example of a binary search tree that is not an AVL tree, you can look at this one. This is something that was created by our insertion algorithm, and it's not an AVL tree. Definitely forced to change my insertion algorithm. Okay, see you tomorrow.